All right, so let's keep cooking here. All right, so for today, you should have finished up that tutorial, putting up kind of a scoreboard and stuff like that behind it, right? So I'm not going to go and duplicate that. That's kind of not that big of a deal stuff. We'll end up incorporating into um, our app. But I will finish talking about some of the stuff we were talking about last time. Um, just kind of operating off of some of the things in the code. Let me get back in here. So one of the things we introduced this last time was something called a design pattern, which is a proposed good solution to a common problem, where common problems can mean all sorts of different things depending on the direction you're coming from. And good solutions are also in the eye of the beholder, right? What seems like a good solution to one might not be that great of a solution for somebody else. But in any case, we got these things called design patterns, and we have a zillion different design patterns, but a couple of them, well, more than a couple, some design patterns have kind of floated to the top as being very commonly used ones. And one of them was this idea of MVC that we see over and over and over again inside of various technologies. You see this in Android programming. Actually, you basically see it in every single example of modern computer programming. You know, the idea that it's a good idea because now our modern day computer programs keep getting larger and larger and larger. It's a good idea to organize these in a reasonable way. Keep your logic in one place, your interface in another place, your data in a third place. And that way you have things relatively organized, but then you have to have some kind of interesting way to connect those things to each other for when there does need to be communication between them. We saw this, we saw the way Unity implemented this. Remember, a design pattern is not actually an implementation. A design pattern is an idea, it's a suggestion. So when when Google made their Android Studio product, they implemented the MVC design pattern in there in the way that made sense to them. When Microsoft wrote Visual Studio and their interface builder thing for C# and stuff like that, they implemented MVC the way that made sense to them. We're seeing the way Unity did it in a way that made sense to them, so on and so forth. All right, so in Unity, let me just go in here and get one of our scripts open. Get our player controller opened here. I also brought a normal mouse because hopefully you've recognized so far sometimes when you're manipulating the 3D space, a normal mouse works a lot better than a trackpad. You can pull it off with a trackpad, but just something to think about. All right. Well, so if we look at our player controller here, and we notice we have, this is the normal class, just like any other class that we've seen. This guy just happens to inherit from mono behavior. We talked about that last time. Mono behavior is the thing that says, make this compatible with Unity so that certain functions get called once per frame, and there's a start thing that gets called, those kind of things. We are going to be writing classes here that we are not intending to be part of the Unity side of things, but we do want the logic to be there, our data structures, keeping track of our rooms and our dungeon and things like that. So we'll see that by example. So we won't always inherit from mono behavior inside of Unity, but anytime we would attach this, if we want our script to attach to a game object, it has to be a mono behavior. Otherwise, it won't attach. That component won't hook up. All right, so as we do with most classes, we see that our fields are largely private. Remember, we have public, private, protected. We want to make things private initially, then loosen the reins as it makes sense. But with public is the way that Unity implements MVC by allowing us to write some code that we want. So this is our controller part of MVC. It allows us to write some code that allows something from our controller to be communicated over to our interface, our view in MVC. So I have this variable called speed. That's a floating point variable, and I've made it public. And because I did that, When I click on player and I go down to his player controller, we see this variable here called speed. All right. Making it public is the way they've implemented MVC. Make some sense? All right. Kind of unimportant how or why they did something like that. It's just that they did. And if we want to have access to that thing inside of Unity, that's how we have to play the game. All right. Make things public. All right. We also talked last time about this idea of generics, where inside, so we saw it through an example of our game object. So we look over here in Unity and we pick a random game object. I've been using player since we have a bunch of stuff in there. So I select my player game object. Over here on the side, we have a collection of components that belong with this game object. Okay. Now this collection of components, there's a bunch of different components that are in here. We have a transform, which is a vector, well, a transform is a transform. It's a collection of vector threes. We have a mesh filter. We have a mesh renderer. We have a sphere collider. We have a rigid body. We have a couple of, we have a player input module. We have a couple of, well, we have a script. We have a material. So basically what I'm saying is the collection of components associated with a game object, that Santa bag holds all sorts of different stuff. All right. So when we throw stuff into our bag of components, the bag of components is written generically to hold anything that's an object. So imagine behind the scenes here, the people at Unity who were creating this, this program, when they said, okay, we need to have a collection of our components, they said, well, we have 30 different kinds of components. I think there's actually more than that, but we have a zillion different component types. Yet I want to put them all inside of a single container, single, list. So in order to do that, I have to drop down to the most generic form of a component. And we've learned in object-oriented programming, the top level object is usually called object, right? So what we're going to say is these are, these zillion different components. They're each unique in their own way, but we're going to pretend like they're all generic objects. All right. And because I'm going to pretend like they're generic objects, I can get one giant bag and throw all of these guys in there because I'm treating them as a collection of objects. Okay. Or perhaps behind the scenes, they've actually made, it's a collection of components where then we have a zillion different types of components. Same logic would follow here. When I put them into the bag, they were individual, right? I have mesh renderers, colliders, rigid bodies. These are all different types of components. But when I put them into the bag capable of holding generic components, they lost kind of their identity. All right. Now, they still are what they were. Okay. But in terms of the way they're stored, we no longer have their exact identity. So that when I take them out of that bag, they come out generically. So when I remove that rigid body component from the bag of generic components, it will come out kind of, let's think about it as blurry. All right. It is still a rigid body. What's actually under the hood, what's stored at that memory address in your computer is in fact a rigid body, but I currently have it in a variable that's of type object or generic component or something like that. He doesn't automatically have all those functions, or at least C# isn't convinced that he has all of those functions available to him. Because as far as C# is concerned, it's a generic object. So I have a couple of options. I can get something, and actually the way the way generics is used for the component, you actually can't do what I'm about to say, but just keeping it as generic as possible here. We have a couple of options. We can remove the component from the bag. Let's say we're removing the rigid body. It comes out as a generic component. Now I might know it's a rigid body, so I can then typecast it to a rigid body because I know that's what it was. it happens to come out of the bag as a generic component because I had to define my bag as being capable of holding all my different kinds of components. Okay. If I only taught it how to hold rigid bodies, that's all I'd be able to put in there. I had to teach it how to hold all the different things. So I had to drop to the lowest common denominator of all of them, which is either object or generic component, however they implemented it. So now when it came out as a generic blob. I can then re-give definition to it by casting it to rigid body and say, you are now a rigid body. Okay. But the way we accomplish that here in Unity is we utilize this idea of generics. When I ask, let me just check something real quick. This dot game object dot get component. Okay. So notice here. Yeah. So we actually see it. So notice up here, there is a version of get component here. So you actually can do what I was just suggesting. So we'll actually do it. Well, we'll have to give the system type. So I'll just talk about it out loud. So there's a version of get component that does not require me to pass in the type of element that I'm looking for. Instead, I can give it the type here as a parameter, and it will come out as something of type component. So a couple minutes ago I was mentioning, well, it's going to be whatever the lowest common denominator is, either a generic object or maybe it's a generic component. It is a generic component. All of these things are components, whatever the minimum commonality is between all components, that's what these guys come out as. So there's a version of get component that will allow it to come out as a, get back, that'll allow it to come out as a generic component. I could then convert it by putting in parentheses ahead of it, rigid body, and turn it back into a rigid body, re-give it definition. All right. But with generics, we have the ability to say, all right, I want to get a component here. Well, what component do you want? I want your rigid body component. So I'm not going to actually tell you the type I want here. Instead, I'm going to do it through the generics, call it protocol. And what that'll do is when I return, when the value comes out of here, it will come out as one of these. It will have its definition. Realistically speaking, the way generics are implemented is probably just typecast it to rigid body. It's done what you would have had to do manually. It's just done it for you so that when it flies out of here, to get set into this variable, it will come out of here not as a component, but as a rigid body, which is a component. I can then store it in a variable. In this case, my variable is called rigid, is of type rigid body called RB. So he comes out as the actual type of component we're dealing with. All right. So again, this isn't a Unity lesson. This is a modern programming lesson. This idea of generics, whenever you see these little angle brackets in modern programming languages, start thinking about this is probably a syntax related to this concept of generics. All right, so let's see, what else do we talked about the on move last time. So this is that callback function thing where I think I probably connected it to like with our smartphones, you have like push notifications turned on. You want to know when the Packers score or something like that. Pick your favorite sport or whatever, so you might have notifications turned on so that whenever something that you might be interested in happens, you get a push notification to kind of, nudge you, right? So that would be event-driven programming where we get notified. In this case, we want to be notified whenever a player, whenever some game object that has our player input component in it, we want to be notified whenever that thing has moved. Okay. Well, actually, that thing wants to move is actually really what's happening. So whenever we push the arrow keys or something, that creates this event that lets our script know that this guy wants to move. Just FYI, if you'd like to make that actually happen, write some code. All right. So that's what this callback function is. So by adding that component here to our player game object, we effectively say we are interested in push notifications related to that game object being interested in moving. Okay, so this on move function, and this is a naming convention that you commonly see in most modern programming languages. So like if you've done web programming with JavaScript, you might have used something called like on button click or on button clicked, maybe it is, which is, you want to know when somebody hits a submit button or somebody hits one of the other buttons. And what it does is when they hit it, that event calls back to some code that is the handler for that event. Okay, so we handle events. So we write the code generically. In here, we're saying, hey, when and if, because there's a possibility that the user never actually calls this code, right? We never touch the arrow keys. This event never is going to happen. So when/if so the game object wants to move as a result of us pressing stuff on the keyboard, this function will get called, which then allows us to respond. Okay, so it sends not only, it raises this event, the on move event, it also gives us some information about how it wants to move. All right, so we're going to take that information, we're going to grab the vector2 from it, which is the X and Y coordinates of how it's going to move. All right, we're going to go ahead and store those in fields. That way we have access to them outside of this on move function. Because right now, movement value, this guy right here, his scope lives and dies with on move. We don't have access to him outside of this. So if I want to ultimately be able to do something with that value on the next fixed update, remember fixed update gets called 60 times per second or 60 frames a second. So in the next 60th of a second that I have an opportunity to do something here, if I want to have access to the most recent move information, I have to put it in some variables that I have access to outside of this function. All right, so I've made my movement X and movement Y. I've made them fields in this class, which effectively makes them globally available everywhere in this class, which means I can reach them inside of on move, but I can also use them inside of fixed update. Okay, and again, I like putting this dot in front of the stuff, even though we're seeing here it's not needed. All right. So inside a fixed update, the next 60th of a second, when this guy gets called after we've done whatever we're doing inside of on move, we're going to go ahead and grab, well, we're going to go ahead and build a vector3. Remember we talked about vector2s and vector3s last time. They're scary ways of saying X and Y coordinates versus X, Y, and Z coordinates. We're storing it in either a 2-bucket or a 3-bucket array. That's what vector2s and vector3s are. 2-bucket or 3-bucket arrays. So we're going to go ahead and create a new vector3. This vector3 is going to have our X coordinate in the X. It's going to have a 0 in the Y. The Y in our 3D space is the up and down. And it's going to have a our movement Y is going to be in the Z space for us to go the in and out. Okay, so Y is the in and out, the X is the side to side, and the Z is the in and out, the X is the side to side, and the Y is the up and down. All right, so that's why we've used our movement on the Y as our position on Z. All right, so we'll go ahead and build a vector3 out of those two values, throwing in a hard-coded 0 for our up and down. And then what we're going to do, so we have this representation of a force. How hard are we pushing this value forward and over either direction? Okay, that's what our vector3 now holds. We're now going to take that vector3. We're going to take our rigid body, which is the physicality of our game object. So that rigid body is the rigid body component that we added to our player game object. So that guy has a physical presence that physics can act on. And we're going to basically shove him. Okay. How hard and in what direction are we shoving him? Well, we're shoving him in the direction represented by our vector3 there. So it's some level forward or back, and it's some level left or right, just not up, not up and down. And how hard are we shoving him? Well, what we do is we take whatever our speed is, it's just a multiplier of how hard. So the harder we shove you, the faster you move in that direction, right? That's why we called it speed, right? The reality is the speed holds a multiplier, where if we barely shove you just in that direction, we just give you a little nudge. Every 60th of a second, we give you a little nudge, a little further nudge, a little further nudge, so on and so forth. Not going to move very quickly, but if we put a multiplier on there with speed, you'll move harder in that direction, because this multiplier ends up being, this is linear algebra. We're multiplying a fixed value by a vector, so every element of that vector will be multiplied by speed, which translates into us shoving it harder in that direction. Make some sense? Physics engine does all the magic for us in terms of how hard it gets shoved in that direction and what happens to that rigid body after it's been shoved in that direction one time. All right. And we see that happen. So if I run our game here, whatever my speed currently is, I just press the up arrow once. All right, I pressed it one time, and he is moving, not very hard. That my speed set at. Okay, my speed is 10. So he is moving. We should actually see him, I would think, slightly slowing down. Eventually he'll stop when he hits that wall. All right. But if we look at our rigid body here, we notice that a rigid body has mass. It also has a level of drag, something called angular drag. These are all things that if you were to take a marble and put it on this surface, and I just gave it one little push, that marble has some level of resistance with the surface underneath it, so it sort of kind of will slow down from the energy I gave it. All that's being simulated here with this physics engine. All right. But if I keep pressing down, we notice that that force continually gets added. Right. So we're seeing how, and this is updating every 60th of a second as this guy is moving around. All right. So we're modifying the direction and strength of our force. So even though as I push it in one direction, that guy is probably technically slowing down based on the resistance of the ground, you know, it doesn't take a whole lot for me to get him stopped. All right. So that's kind of what's going on there with us utilizing that rigid body and shoving it effectively. Okay, finally, we have this thing called a trigger. Now, this has to do with colliders. Let's go in here and add colliders to our notes. When two colliders interact, something can happen. If a collider is a standard collider, then the physics engine will, I'm going to just call it, simulate the collision. All right. And we can see that if I go back to my program and I run it. And I just drive this dude into the wall over here. We see that he slammed into the wall, kind of bumped back. We believe that the physics of that, the math behind that was calculated, and we saw a simulation of what would happen to this ball as it rammed into the wall at that speed. Okay. Now, as programmers, though, we can choose to make it work differently. So inside of our collectibles, so we learned about two different things with our collectibles here. One is something called a prefab. So prefabs allow us to create a game object and all of its, call this specialness once. So that's all the components and the scripts we attach to it and all that stuff. And then add it to a collection of prefabs that can quickly be brought into our game whenever we need it. And we can instantiate prefabs programmatically if we want. We'll do that at some point. But we can also, as you did on this one, just drag them out, multiples of those out and move them around and that kind of stuff. Okay. So that's what a prefab is. It allows us to design something once when you're going to have multiple of these. Think back to like if you've played Super Mario Brothers or something, you know, all the little mushroom guys behave the same. All the little turtle guys behave the same. Then we have turtle guys with wings. They behave the same, so on and so forth. So those were probably prefabs. And then whenever a mushroom guy needed to come into existence, they drug it out there, and that's the behavior he had. Okay. So prefabs are a way of us accomplishing that. So what we did here, I built the prefab, whatever, you did the same thing. So all of these guys are basically the same. Well, they are the same object. All right. They're just in different locations. So they're multiple instances of our collectible prefab. Now we noticed here that those collectibles, they came with a box collider. All right. Now, if I go into my actual prefab here, and I change that box collider to no longer be a trigger, I just turn that off. Now, all of my other collectibles, they will now have that turned off. So I updated the prefab itself rather than a single instance of it. If I modified a single instance of it out here, I can make a change and I think there's a way for me from here to tell it to update everything. So I can say that this guy I can say apply all to those prefabs. So I could accomplish this by updating one thing in my scene and then saying it to apply all. But similarly, I might have like the boss collectible. He's giant collectible, maybe he has weapons, that kind of stuff. So he might behave as a normal collectible, but then he has some extra stuff we add to him for him being more powerful or whatever. All right. So that's one possibility that you can do, where you can have a whole bunch of things that behave a certain way and then have one outlier that you modified a little bit. All right. So we'll turn off our trigger on our box collider. Let's make sure this guy is still turned off because I kind of disconnected him from those. We can go up here. We can tell it to revert if we want back to its original state. So I'll actually do that. Okay, so now all these are in that state where the trigger is turned off. So when I turn the trigger off, what we're saying is we want you to just make physics happen, whatever that means. Okay. So now those guys are no longer triggers. So now I bump into it and physics is happening. So you might say, well, I wrote code to make it disappear. Well, why isn't physics happening and then it's also disappearing? Well, it's because of where I put that code. That code is inside of a callback function. I am interested in the event associated with a trigger being entered. So the name of that event was called on trigger enter. And at this point, I'm not interacting with anything that is a trigger. Therefore, triggers are never entered. Therefore, that code never gets called. Therefore, the game object never gets destroyed. Make sense? So if it's not a trigger, it behaves as a physical thing and just physics is applied to it. If instead we make it a trigger, and then I run this, what we effectively just did is we said, turn off default physics behavior. And instead, let me programmatically handle what should happen. So now I drive towards this. He didn't bump off it or anything like that because we turned off physics. All right. And what ended up happening is we now are responding when we turned on trigger, it now will send out an event when that trigger is entered. So anything that has this player controller associated with it, he will get those responses as well. So we get our on trigger enter. It's we ask ourselves so we bumped into another collider. So notice that it's colliders that interact with each other. So inside of our player, this player collided with another thing. We asked that other thing, is that other thing's tag called pickup? All right. So we can kind of label things as some, with tags. So we might want certain things to happen when we interact with the ground. We might want something else to happen when we interact with the walls. We might want something else to happen when we interact with something that's a pickup, things like that. Okay. So we might have, all our monsters. So maybe, think about Mario Brothers, the mushrooms, the turtles, all those guys might be flagged as enemies. So if Mario collides with something that is an enemy, bad things happen, right? If he's a bigger guy, he becomes a smaller guy. If he's already a small guy, he dies. That kind of jazz. All right, but that isn't what happens when Mario jumps up on one of the pipes or something like that. Okay, that's a collision that is not something we want to kill him off from or something like that. All right, so we can use triggers to separate our game objects and allow us to programmatically say, what are we interacting with and what do we care about? We don't even have code in here for dealing with the ground, but we could. We can make it so that whenever it deals with the ground, we already know how to add forces. We can just build a vector 3 that takes whatever his current location is and then maybe pops him into the air like he ran over like Old Faithful or something like that. We shove him with a Y value in the positive direction, and he flies up in the air. And that would happen constantly as he bumps into the ground. It would happen. There would be pauses because as he was thrown into the air, he wouldn't be colliding with the ground anymore. But it allows you to have some fun things with it. But that's how on trigger enter works. If I go over to my rotator and I go to on trigger enter, so notice that it wrote that for me. I think I tried to show that a couple classes ago or something. It was behaving funny. So sometimes closing Visual Studio and reopening it, you can get it to go ahead and write your your thing here, so you don't have to look it up in documentation. And what I'm going to do here is I'm going to say print. Now we could do the whole force thing too, but to say I have been collided with. So now we taught our rotator to also be interested in trigger-based behaviors. So whenever a trigger is entered associated with this guy, this will get called as well. So might be a tie goes to the runner type thing, but the script will execute this. So as the player is killing off the game object that he bumped into, because keep in mind, that is what's happening here. Our player currently becomes aware when he bumped into something. And if the thing he bumped into was one of those pickup things, he's then going to deactivate that pickup thing, which removes it from the scene. Actually, it doesn't remove it from the scene. It just turns it off in the scene. Okay. So, but that's all happening from the player's perspective. If I'm inside the player controller script here, it's as if I am, in this case, we only have the player controller script attached to one game object. So it's as if I'm that game object and it's me reacting to whatever hit me. So the player is pointing at the pickup saying, deactivate, deactivate, deactivate. The pickups themselves, they have that rotator script associated with them that makes them spin around, do the rotation thing. So I'm now teaching him to also be interested in when triggers get entered. And it doesn't matter what he collides with. Because remember, he's the one who actually has the trigger. But it doesn't matter what he collides with. This is always going to get called when he collides with anything. Now, all these guys, I think, are floating above the ground here. So they actually, the only time they should get in contact with another collider is when the player bumps into them. But when the player bumps into them as they're disappearing, we're going to see out at the console them say, I've been collided with, proving that this guy gets updated as well. All right, so now we have multiple dudes who are interested in these collisions. I'm going to go ahead and run this. All right, and then I'm going to click right here where it says console. So that'll allow me to see those print statements. So sometimes you might want to do some debugging stuff, or you might be interested in why is it behaving a certain way. You want to know what the value of something is. We have several different things we can look at here. You might look at the transform over in the inspector or something, but maybe we just write it down there. So notice there when I ran into it, the player is deactivating them, but notice I have stuff printing. Each of those pickups is displaying to the screen here, I have been collided with, proving that their version of on trigger enter has also been hit. Make sense? And if I were to lower him down so they kept bumping into the ground while they were rotating, then it would be printing that often because they wouldn't be getting killed off. So every single time the trigger was entered when one of their points, hits the ground or something, it would go off. All right, so updating the notes here. If a collider is a trigger collider, then the programmer gets to decide how it interacts with the other with the colliding collider. I think that's technically accurate. All right. So two different versions of colliders. Let physics do its thing, whatever that means, or hey, let me programmatically interject. All right. If we want to have some physics-based stuff, we can still do that. We can apply a force to it. We could even the player. We take the on trigger enter out of here. The player controller, if he runs into something called pickup, we could grab the rigid body from that guy. We could throw it up into the air and then, set a timer every, maybe after 3 seconds or something, then it gets destroyed. So we can add some physicality to it or something like that. There's also some things, if you think about how like Super Mario Brothers works, when Mario dies, what do we see? What happens if you've played Super Mario Brothers anytime recently? So Mario is a little version of Mario, runs into a mushroom guy. What happens to him? He falls down, but if you look at him next time you do it, what you see is on the screen when Mario is running, he's turned sideways, right? So he's either facing this way or facing the other way. All right. But when he dies, he pops up in the air and he's like this kind of look. He's looking at you with the screen. Okay. The way you implement that in Unity is something called a ragdoll. Okay, so he's no longer as a generic game object, so he's kind of lighter weight than that. And instead, what we do is we throw the ragdoll up in the air, and that's the thing that drops down. So all of his scripts and stuff are turned off. But that's how we handle his change in orientation. Because otherwise, if you're going to the right, Mario's facing to the right. If you're going to the left, Mario's facing to the left. There isn't a way to get Mario facing you when you're controlling except when you're standing on top of a pipe. When you go down a pipe, I think he faces you. All right. So in any case, these are just ways they're accomplishing those things. But that was way before tools like Unity existed. So, original Super Mario Brothers, they just wrote that, right? They wrote all the programming for that stuff. That's why old games like that don't necessarily have overly accurate physics, right? That's just because they had to program the response that was going to happen when something bumped into it or whatever. Okay, so let's see, anything else I want to talk about in here? For rotator, this is kind of an interesting thing. So remember that this update function, as opposed to fixed update gets called every single frame. Fixed update gets called 60 times a second to kind of emulate 60 frames a second. You can decide what makes sense for your particular game or what you're doing inside of the update function. So in this case, every single frame, we are telling this particular game object to set his transform, to do something to his transform. Okay, so this game object, we're going to take his transform, and what are we going to do to it? We're going to rotate it. And we're rotating it how? Well, we're going to create a new vector 3. We're rotating it about this X, this Y, this Z. This is how we're rotating it. All right. I probably mentioned last time, or at some point I maybe mentioned it. Rotation is actually fairly complex in game engines. You probably want to rely on the game engine doing the rotation math and stuff like that for you. It does something, the math for rotations uses something called quaternions, and we'll eventually be working with that, but let's just call it hard math. All right. And it's one of those things that let the game engine do the hard math for you so you don't have to. All we're telling it is we want this thing to magically rotate this way. All right. Now, remember, just as we applied a force over here to our player controller, so when we on update, if our movement has changed, we are adding a force to the rigid body component of our player. And how is that force modified? Well, we're saying this is the direction we want to shove you, but we're going to multiply that by how hard we're going to shove you. All right. And this gives us our overall shove force, if you will. When we go back over here to update in our rotator, notice that we are rotating it about these axes, in that angle on those axes. But we're multiplying it by time.delta time. Anybody know what this means? I'm sure it was in the tutorial, but did you look into it very much or follow it? What does time.delta time mean? And I realize when you're doing a tutorial, you're mostly watching the videos, duplicating it. So that's where I'm adding in color commentary here. So time.delta time is pretty important. Or it's at least one of those things that we can use often. Oop. So time.delta time is how much time has elapsed since the last time this was called. That's the number it gives you. So realistically, if it's inside the update function that gets called every single frame, not a lot of time has collapsed or elapsed. Make sense? All right. But it is still a measurable amount of time. So what we're interested here is we want to keep this thing rotating, but we only want it to rotate an amount relative to the last time we rotated it. Make sense? And since this is happening every single frame, think back to like when you were a kid, you had the little flip books, right? The pictures, you flip through them and you see it happening. That's how animation works, your cartoons and stuff. Okay. That's what's happening here is, let's call it 100 times per second on a, we're not dealing with earth-shattering video games here. All right. So let's say 100 times per second that update gets called, which means that 100 times per second, we're going to rotate it just a teeny bit. And because it's happening so many times in a row, we see it as a smooth rotation. That makes sense? But time.delta time gives us the ability to work with that, the partition of time that has happened since the last time we did something related to time. Make some sense? Okay, so pretty important tool for video gamey stuff when you want to have smooth rotations. The other thing you could just do is you say, look, we're going to rotate it once. We're just going to slap it in a rotation direction really hard. And eventually it'll slow down, but there's not going to be a whole lot of resistance since it's just in the air. So it'll just be spinning like a top. So instead of us rotating it a little bit each frame, we're just get it rolling, and we'll just test it and hit it hard enough to get it spinning in the speed we want it to spin. So what's kind of fun about working within something like Unity is you kind of get to mess around with what's the right way to get the look you're interested in. There isn't necessarily the one way of doing things. There might be correct ways of doing things. And eventually, as we start getting more and more stuff going on, we probably won't run into it in our game here unless we force it. So at some point, we will force it when we look at instantiating prefabs ourselves. But at some point, what ends up happening is you get too much stuff. You either have too many game objects happening at once, which each one has scripts. You have too much stuff happening inside of the updates that your game starts bogging down. It starts getting sluggish. All right. And this is kind of, if you're a PC gamer and you, and when you built a computer, I think I asked the question here, how many of you have built your own computer for PC gaming before? Wasn't there a couple people? Yeah. So when you were building your computer, you were really shopping for probably three things were the major components. You got fast memory just because you wanted to pay too much money for memory with the heat sinks on it. Chances are you wouldn't notice a difference, but technically at the tiny level there would be. But really it's the CPU versus the graphics card. Now, which is more important? Well, most gamers might say, well, the graphics card is more important. And that's probably a true statement, but you still want to have a CPU that is strong enough. The faster your CPU is, the more game objects it can deal with at once. Okay, because it's having to call each of those update methods and do something each time through and things like that. Does that make sense? It's those two separate things that are happening. The amount of memory is how many game objects can even exist. Right? More RAM you have, the more stuff you can remember at once that's on the screen. We have all sorts of strategies in our video games where next time you're playing a game, if you're a gamer, you're probably already aware of this, but if you look at something that's close up on your screen, it's very detailed. You look at the trees in the distance, they get more blurry. It doesn't fully render things that are far away because we care less about them, right? That way, so you're trying to minimize your computing power to the things that the humans actually paying attention to. This is where it gets fun in virtual reality because we have this thing called foveated rendering. The headsets that have eye tracking on them, they pay attention to where you're actually looking. And where you're actually looking, they spend all their horsepower making that look really good. Because when you're not looking, you're not seeing. so it doesn't have to make any of that look good. All right. So that allows you to squeeze more out of less computing power. So that's going to be kind of an exciting thing that's happening with that. All right. So questions about this stuff. All right. So what I want to, I'm just going to add a note here. I'm not going to give you homework for next class, but I want to start with, say start, well, I'll put it in it. So I want to start with singleton. So next time we're going to be talking about another design pattern called the singleton, because we want to start thinking about how can I make different game objects communicate with each other. If I have two things because right now we have communication kind of accidentally happening when they slam into each other, right? Player hits the pickup thing and things disappear. But I might want things, to actually be communicating with each other without having to respond to a collision. So we'll talk about ways we can accomplish that. Questions, comments, concerns, bribes. All right. I will see everybody on Wednesday. What's up?
When they were making the whole video game, what was their version of like?
Nothing. They just wrote it in C or C++, and yeah. So they probably wrote their own library for things they had to do often. They wrote functions for those, like you know, they probably had the when Mario dies function
Yeah.
where, you know, okay, you got hit by something, call that function that makes them pop up onto the screen or whatever. But they had to write it, you know, so they wrote their own physics engine, if you will, but only the aspects of it they needed. As opposed to a tool like Unity that can do 4 zillion things and we use 8 of them.
So then like, well then like what they use for like